are back today, and we will be going over power series and really what a power series is. So right now in this first problem, we're going to be looking at the very basics. What is a power series? So the power series is basically a series where n equals 0 to infinity of c sub n x to the n, where c sub n is a coefficient and x is a variable. And most of the time when they ask you about these power series questions, a lot of the time they're going to be asking for the interval and the radius of convergence. So basically, for what values that x is equal to, for what values of that will the series actually converge? So that's what we'll be doing in this first problem, and we're just going to be trying to find out the interval and the radius. So moving on to this problem. So the series has n equals 1 to infinity of negative 1 to the n times n over 4 to the n times x plus 3 to the n. So really what we want to do first is we're going to use the ratio test, and that's a really good strategy to use for a lot of these problems. And remember, the ratio test states that when you get an x, that for every value that x is less than 1, that means that it converges. So that's what we're going to be using. That's the theory that we're going to be using. So if we go ratio test and we go limit as n goes to infinity of absolute value, and I just like to write these out. So remember n plus 1, so it's negative 1, n plus 1, x plus 3 to the n, x plus 3 over 4 to the n times 4 times 4 to the n over negative 1 to the n and x plus 3 to the n. Sorry, that's a little bit squished, but we can see that these will cancel out. This will cancel out. This will cancel out, and we're left with limit as n goes to infinity, negative 1 times n plus 1 times x plus 3 over, over 4 times n. So we can plug this x plus 3 out, limit as n goes to infinity. And because it's an absolute value, the negative 1 goes away, obviously. So it's going to be negative n plus 1 over 4 to the n. Quick l'hôpital will get 1 over 4. So we're going to find out is that x plus 3 over 4 is less than 1. And that's really what we're trying to find out, right? So for every value of x that makes it less than 1, that's when x is going to diverge. That's when the series is going to, that's when the series is going to converge. So to find the radius, all we do is multiply that by 4. X plus 3 is less than 4, and this value is going to be our radius. So the radius of this will be 4. But the interval will be something different. So the interval, we have a lower bound and an upper bound. So the lower bound is also going to be, so essentially that's going to be like greater than negative 1. It's going to be greater than negative 4, because we multiply that by 4. We're going to get x less than 1 greater than negative 7. And basically what we're going to do here is something that you've already learned in your previous lesson, so I'm not going to go over that too much of that in depth. What you're going to do is you're going to test for when we plug negative 7 in for x into this equation, will this series converge or diverge? And if this series converges, then we're going to do less than or equal to, greater than or equal to, and if it diverges, we're just going to do greater than. Same thing for 1, we plug 1 in for x into this series and to see if it converges or diverges. So I'll give you guys, so I really recommend that you pause the video right now and solve that out. Alright, so if you solved it out correctly, you should have gotten the interval is negative 7 to 1. And that's how you find the radius and interval of these type of problems for power series. Now we're going to be looking at a different type of problem, a different type of power series problem, where it says use differentiation to find power series form. So they give us an equation f of x equals 1 over 1 plus x squared, and we're supposed to represent that as a power series. So first, I'd like to strongly encourage you to write this as 1 over 1 minus negative x squared, okay? So in order to write this as a power series form, we're going to be looking at stuff that we already know. We know that 1 over 1 minus x will be written as the summation of n equals 0 to infinity of x to the n. But we want to get this looking like this. So what we're going to do is we're going to take the derivative of this. d dx will get us 1 over 1 minus x squared, and the series will be n equals 1 to infinity of n times x to the n minus 1. So we basically take the derivative of this, so it's nx, always lower this by 1, n minus 1, and now it's n equals 1 because we need to get this to equal 0, and when we plug 1 minus 1, that gets us to 0. Now, these still don't look exactly the same, and the difference is this negative x as compared to this. So what we're going to do is we're going to just simply plug in a negative x for that. It's really not that difficult. So we get n equals 1 to infinity of n times negative x to the n minus 1. We don't want to leave it as that. We want to simplify it even further. N equals 1 to the infinity of negative 1 times n minus 1, because the first term is positive, times x times n times x to the n minus 1, and this is how you represent this function as a power series.
So we're going to evaluate x cosine of x cubed as an indefinite integral. So the way we're going to go about this is we're going to use the identity that we know, which is that cosine of x equals a summation from n equals 0 to infinity of negative 1 to the n times x to the 2n over 2n factorial. So we kind of know this as a rule, so we're just going to use this to help us solve this. So all we're going to have to do is just plug in the x cubed for x here. So you're going to get that cosine of x cubed is going to equal the summation of n equals 0 to infinity of negative 1 to the n, and then x cubed to the 2n over 2n, and this should be factorial, 2n factorial. So then we're going to have to simplify this up a little bit more, and it's going to be summation of n equals 0 to infinity, negative 1 to the n, x to the 6n over 2n factorial. So we know that this represents the cosine of x cubed, but then we also have the x to plug in. So we're going to multiply the x in, right? So this is just going to become summation of n equals 0 to infinity, negative 1 to the n, x to the 6n plus 1, because of the x that we multiplied in from here. This is going to be over 2n factorial. However, this is just the power series for this right here, but this is going to be the integral of this. So the way you take the integral of this is just kind of like taking the integral of any other function with respect to x. So this would be the summation of n equals 0 to infinity of negative 1 to the n and x to the 6n plus 2, because that's how you integrate. You add 1, and then you divide by 6n plus 2, and then the 2n factorial just remains as it is because this is with respect to x, right? So this with respect to x equals just this. So when you evaluate this x cosine of x cubed dx, this is an indefinite integral, so we're just going to have plus c, and this power series represents this. So that is the final answer. We'll be evaluating the limit as x approaches 0 of x squared e to the x, or x squared times e to the x, over cosine of x minus 1. So the way we're going to go about this problem is we're going to plug in the Taylor series for e to the x in cosine of x. And this can be determined just using the information that you know about the Taylor series, but we're just going to skip that to make this a little bit shorter. And we're just going to write out that the limit as x approaches 0 of x squared, and then we're going to plug in the Taylor series for e to the x, which is going to be 1 plus x plus half x squared, and then just so on. So we just get the general idea of what it looks like. And this is divided by, and then we're going to plug in the Taylor series for cosine, which is going to be 1 minus half x squared plus a fourth x, so this should be factorial right here, x to the fourth, and then minus 1 over 6 factorial x6, and it's going to be so on, and then minus 1. So now what we're going to do is we're going to see what things kind of cancel out. So we know that this 1 right here and this negative 1 are just going to cancel out, so these go away. And then here you can't really cancel anything out, but you can just multiply the x squared to all the terms. So then you get limit as x approaches 0 of x squared plus x cubed plus half x to the fourth, and so on. And this is all over negative half x squared, which is just basically all this right here. So I'm just going to write it out. And then, so now you're just going to have to, you can divide everything by x squared. So this would be over x squared, so this just becomes 1, excuse me. And then this divided by x squared, this just can become x, and then so on. So this just can become x squared. So then everything here divided by x squared, these two cancel out, and this just becomes x squared, and this will become x to the fourth. So the only constant we have throughout this whole thing is going to be the 1 over the negative half. Because the rest of these are just going to, as the limit approaches 0, these are all just going to become 0, and these will all just cancel out. So limit as x approaches 0 of this function right here is going to equal 1 over negative half, which just equals negative 2. Okay, so we're going to represent x ln of x to the third degree centered around a equals 1. And we're going to use the Taylor series to help us out. And Taylor series just says that the summation as n equals 0 to infinity of f of n times x minus a, which is what it's centered around, to the n over n factorial. This is how you represent a function using the Taylor series. And then the Maclaurin series is basically the same thing as this, except a is always going to be 0, so it'd just be x to the n. But they're basically the same concept. So since we're doing x ln of x, I made this chart right here. And since the base function is x ln of x, that's what f of x is set to. And then you're going to need to find some more derivatives of the function to help you represent it to the third degree. So we're going to take the derivative of this using just like the product rule, kind of like basic derivatives. And this would be ln of x plus 1. Take the derivative again, and you get 1 over x. Another derivative would be negative 1 over x squared. And lastly, another one would just give you 2 over x cubed. So these all represent respective n values of 0, 1, 2, 3, and 4. And so the way we're going to have to find the values for f of n is we're going to plug in 1, because 1 is what it's centered around. So when you plug in 1 for this, you're just going to get 0. When you plug in 1 for this, you're going to get 1. And then you keep plugging in 1, you're going to get, you're going to get 1, and then negative 1, and then this is not very important. So now we're going to have to represent this to the third degree. So these values right here represent the coefficient right here. So for the first one, we get 0, and then x minus a, right? And x is going to be just x. And then a is 1. And then this n value is 0. So you put that there over n factorial, so 0 factorial. So this is going to end up being 0. So this isn't very relevant. And then the next value, the coefficient is going to be 1. And you multiply that by x minus 1. But this time n is going to be 1 over, and then 1 factorial. So this is to the first degree. So we're looking for the third, so we have to keep going. So I'm just going to write it down here. But so the next one is going to be with the coefficient of 1. So it's going to be 1 times x minus 1. It's going to be to the second because of the n value over 2 factorial. And then finally, it's going to be minus 1 times x minus 1 cubed over 3 factorial. And the reason you have this minus is because coefficient has a minus 2. So this right here is how you represent x ln of x to the third degree centered around a equals 1, because this equals 0. So it's just these. So as a continuation of the last problem, we're going to find the error of x ln of x from 0.5 to 1.5, same to the third degree centered around 1. So this is the formula for Lagrange's error, and we're going to apply it to this problem. So the n we're going to choose is 3 because we use the third degree. So R3 of x is going to be less than or equal to f of n plus 1 of x. So this means we're going to use f of 4. So that's going to be the fourth derivative, which is going to be this one. So what we're going to want to do is try to pick an x value from the bound to maximize this function. So since the x is in the denominator, we're going to pick the smallest thing here so we get the largest value. So we're going to plug in 0.5, and when we do that, we're going to get 16. So so I'm just going to write it out. So this is going to be times x minus 1 to the 4th all over 4 factorial. So so this right here is going to be 16, and then this right here, 4 factorial, is going to be 24. And then for this part right here, you're also going to want to pick a value from the boundary, which is going to maximize this area right here. So you can pick 1.5 because these were always smaller. And then that'd be 1.5 minus 1, which is 0.5, to the 4th power. That is going to be 1/16. So that's just going to be your error. It's going to be 16 over 24 times 1 over 16. So the error to the third degree centered around a equals 1 is going to be less than or equal to 1 over 24.